if I can now hand over to my colleague Jenny Bearcock, who is going to talk about the work that we've done on surface water chemistry in the Clyde Basin. Jenny.
And it's really nice to be able to do a presentation that just flows so neatly on from the last one. So thank you, Fiona, for doing an awful lot of my introducing for me. Saved me a job. Okay, so what I'm going to talk about is just go into a bit more detail about the sampling, what was undertaken, where we did it and when, and then discuss a little bit about what influences stream water chemistry, and then I'll show you some geochemical maps, and we'll have a bit of a catchment overview looking at pH and conductivity, and then look at the urban imprints on this, and look at, surprise, surprise, chromium and lead. Okay, so you'll now be familiar with this as the Clyde Basin. So, as Fiona said, there was numerous phases. The first samples were taken in 2002 to 2003 as part of an inner estuarine study, which Dave Jones is going to talk about later on this afternoon. There were 8 water samples taken as part of that, and they're marked on the map in red stars. Then in 2003, in conjunction with Glasgow City Council, samples were taken of the tributaries of the River Clyde within the Glasgow urban area. There's 122 of these samples, and they're a particularly useful and interesting data set because normally our National Geochemical Survey, we avoid urban areas because we're interested in the background natural concentrations, but this is a really useful data set because we can actually look at the urban environment and what effect that's having on waters. Then the major part of the water sampling was undertaken in 2010 when we sampled first and second order streams. There's 1,786 of these, and these we revisited the sites that were visited in the 1980s for the sediment samples which Solvi talked about yesterday. And at the same time, in 2010, we also took samples of the major tributaries of the River Clyde and also the River Clyde itself within about 500 metres, both upstream and downstream of the confluence with these tributaries, and there's 60 of these samples. Now I've marked in stars all the samples which fall along this linear feature that is the River Clyde, and I'm not really going to have time to discuss them much after this point, although there is a bit more information on one of the posters outside. In the dots is the stream and the urban data sets which we've combined, and we'll consider these together as they form a continuous coverage of the Clyde catchment. So at each sample site we took both filtered and unfiltered water samples. The unfiltered water samples we dealt with at the time in the field, and we analysed these for pH, conductivity and alkalinity. The filtered samples, we filtered them to 0.45 microns, and they were taken back to the labs and they were analysed soon after each individual sample phase. So I'm just going to discuss a few aspects of stream water chemistry. There's numerous influences, and they're all sort of completely intertwined. They include both rainfall amount and chemistry, solid geology, drift geology, soil chemistry, groundwater chemistry, land use and human impacts, and that is a 20-minute talk in itself, so I won't go into all of that. I'll just pick out a few of the key points. So this is a map of rainfall amounts over the Clyde Basin, and the lowest rainfall amounts are in brown and the highest are in blue. And you can see that the lowest amount of rainfall is over the central and eastern parts of the catchment. The highest rainfalls fall over the northern, western and southern catchment boundaries, with the most rainfall over Muirshiels Country Park in the north and the Lowther Hills in the south. Now this is related to topography. All these areas of high rainfall are all upland areas. So moving on to the land cover map, we've seen this one before. So those upland areas that I pointed out, they generally tend to have heathland, bog, semi-natural grasslands, and also coniferous woodland as the dominant land use types. It's also worth noting at this point that where the heath and bog, the purple land use is, that generally tends to be underlain by peat as well, but I don't have time to show you the superficial geology, so just mention that. In the lowland areas you tend to get improved grassland, and also this is where the urban area of Glasgow itself is. So then moving on to the geology, now this is really important in stream water chemistry. In particular, over the summer months when we tend to sample, rainfall tends to be lower, and the streams are kept flowing by a major contribution from groundwater. So therefore the chemistry of the aquifer, which these groundwaters have come from, is really important. Now there's quite a lot going on this map, so I'll simplify it greatly, so apologies to the proper geologists in here, and just talk about the few bits that are sort of easy to identify. So the pink area around here, we've got the Clyde Plateau volcanic formation. It's a hard rock, it's resistant to weathering, so it doesn't contribute many solutes to your stream water, and also that's a major factor in why there's high ground there. Similarly, south of here, this is the Southern Upland Fault. South of this, we've got the older Ordovician Silurian rocks. Again, they're hard rocks. They don't contribute many solutes into stream waters, and they also give rise to upland areas. And here in the browns and greys, we've got the carboniferous sediments, sandstones, limestones, that are also coal-bearing. These are much more easily dissolved. We've got lower-lying land. They'll contribute more to your stream more solutes to your stream water chemistry, and also as well the fact that they're coal-bearing obviously has a major influence on why Glasgow is where it is, and also the fact that you don't obviously want to build it at the top of a hill because that's far too difficult. So, onto some geochemical maps. So, as I said earlier, we combined the urban and the stream water data sets, so we get this interpolated map across the catchment. You can also see we've got proportional symbols which represent the river and estuary data sets, but I don't really have time to discuss those either. So this is a map of pH, and pH is really important in stream water chemistry because it influences the mobility of various elements. And what we can see from this is that I should have said that the most acidic waters are in reds, your sort of neutral concentrations are in orange to green, and your alkaline pH waters are your blue colours. So you can see that your most acidic waters are around your catchment periphery, in particular over areas that are identified as being underlaid by peat. The fact that they are around the catchment periphery means that they're sort of on this high ground. They are where the rocks are resistant to weathering, so they're not going to change the chemistry of the rainfall very much, and rainfall is naturally a bit acidic. It's worth noting that down here we have the Lead Hills mining area. Down here you've got naturally occurring sulfide ore minerals, which are broken up by the mining processes, giving additional surface area, which means that there's extra surface areas available for reactions with the rainwater. And in the case of sulfide ore minerals, this gives rise to acid mine drainage. So what we're seeing here is an impact partly from the natural rocks that are there, but exacerbated by man's activities. It's also worth looking at the urban area of Glasgow. It's generally neutral to alkaline, although it's a bit variable, and you'd expect that in the urban environment given the amount of variability that you get there. So from this point on, the red on the map is referring to high concentrations, and the blue is referring to low concentrations. And this is a map of conductivity. Broadly speaking, conductivity is a measure of solutes, how much is dissolved within your water. And it's a really good way to show an average over the catchment of all the processes that are impacting the water, and of all the solutes, everything that's in there. So what we can see from this map is that around the sort of northern, western and southern areas are where the conductivity is lower. This is a combination of weathering resistant rocks, high rainfall, and also the fact that the land use is generally more natural, and so we don't have many human impacts on that. In the centre of the catchment, we've got much higher conductivity, which is due to the more soluble rocks, and also obviously we've got all sorts of human impacts going on as well. It's worth pointing out here and here, these are open cast coal mines. Here and here, these are downstream of landfill sites, which must have high solutes. So on to a bit of urban. This is chromium. in stream waters, obviously. So, as Fiona pointed out earlier, the chromium is high in the soils because of past industry within Glasgow. And in stream waters, it's an issue because the chromate anion is more soluble at more alkaline pH values. So what with the urban area having a more alkaline stream water chemistry and the waste being alkaline itself, it can be leached from contaminated soils and transported in streams. And finally, this is the lead map. We saw from the soils that the lead, you could sort of really identify the urban area from the concentration of lead, but here you'd be hard pressed to find Glasgow if you didn't know where it was on this map. And that again is because of the pH control. Lead is more soluble in acidic pH waters, and because the waters are alkaline here, what this means is if any lead does make its way into the stream water, it's going to precipitate out and you're going to find it in the sediments instead of in the water. And the last thing I'll point out is we've got lead hills down here. Not only do we have the source of lead in the naturally occurring sulfide ore minerals, but also the stream waters are acidic. So that means that it's maintained in solution and it's mobile and it's carried downstream, and it also affects the River Clyde for quite some time after that. So, like Fiona, I'll advertise our atlas that's coming out soon. So hopefully I've whetted your appetite for that when we bring it out. Thank you.
Thank you very much, Jenny. I think we've got time for a couple of questions. I will maybe ask one actually to do with some of the work that we heard about yesterday, looking at the concentrations of contaminants in mine waters that might be used for other purposes. Have you seen sort of any influences of the coal mining areas in terms of other elements in the water samples that you've looked at?
We have, yes. Unfortunately, because of the nature of open cast coal mining itself, we don't actually have any samples very close to the coal mine because we couldn't actually get access to the land and the streams themselves are diverted. But where we could we do have some samples downstream of these coal mines, and there's numerous elements that, as I pointed out, a couple of those little hot spots, that they do stand out. And of course I can't remember any of them off the top of my head right now because all the maps are all merging into one, but they are two of the things that stand out, sort of map after map. You can see them.
I think you've got maps outside of Sulphate, haven't you?
Yes. Yes, thank you.
Yeah. Okay. Yes.
You sampled your clean waters once, as far as I understood.
Yes.
Did you, just for trying it out, measure the same river over the course of a few months to see how the time variability is, to see how representative your one sample is in the course of the year?
Yeah, well, we always take our samples during the summer months so that the base flow component is dominant, so the groundwater is dominant. And also what we do is every time we're at one field base, we sort of move around over the season. We're generally at a field base for between 2 and 4 weeks. We sample what we refer to as a monitor site, which is a stream which is representative of the area, and we go and we sample it every day that we're at that site, and it's part of the quality control. I mean, unfortunately there's so much behind this that I haven't had time to mention, but it's part of the quality control procedure that all this data is sort of looked at, and if there is anything concerning in there, like if it's really variable, that's then dealt with at the quality control stage.
But we do expect that the data is a spatial. It's a spatial snapshot. It's not a temporal monitoring system. But we do see very strong geological controls over the country, regardless of variations that you may get from time. And again, because of the base flow.
And again, that was something that I didn't really have time. If I had time, I would have showed you the uranium map, which is very strongly correlated to the geology, and that sort of really shows how that sort of stands out.
Did you compare with groundwater quality measurements?
No, we didn't, although I believe there's discussions happening between various people within BGS to look at the groundwater and how everything relates to each other. So that may well come up in the future.
Okay, thank you very much, Jenny.